Okay, let us talk about work, which is more or less the tricky part of Chapter 7. So, we're going to look at some of the easy cases, then some of the harder cases, and some of the hardest cases. We'll get into it a little more in class, assuming we actually, have that once in a while. For a constant force, we're going to define work as the dot product of force and displacement. So, if I've got a box, and I pull this box with some force F, and this box moves through some displacement delta x, then the work done will look like the dot product of this. So, simple case. Let's just take the case where force and displacement are parallel or anti-parallel. So, force is only in the x direction, displacement is only in the x direction. So when I do this dot product, I get x component times x component here, y component times y component, so I get x component of the force times the x component of displacement. These are both positive values if it's going to the right. If it's going to the left, this would be a negative displacement, so this would be a negative work. That's going to be the case where something slows down. So for example, if I have a block sliding along a surface, but the surface is rough and frictiony, the block is going to go some delta x this way, but the force acting on this is probably going to be friction, slowing it down. When the force is in the direction of motion, positive work, increase in energy. When the force is in the opposite direction of the motion, negative work, reduction in kinetic energy. Next worst case, a little more complicated. Let's say the force is off in some random direction. So now we're looking at a box. The box is being pulled up with some force that has an x component and a y component, but is only moving in the x direction. This also equally well could work for a force in a simple direction and a displacement in a complicated direction. We'll talk about this kind of for gravity. Now if we look at this, what we find is that when we do the dot product, x times x, y times y, and this just goes away. So all of this force that we're putting in to lift the box doesn't do anything work-wise. The only bit that goes into increasing the kinetic energy of the box is the bit that's in the direction of motion. So that's, interesting. Kind of has the wonderful idea with the pig problem, where if you have these 3 slides, we're all going to assume that they make it to the ground and they all start at the top. All 3 of these are different paths. But if the only force acting on the piggy, this is the piggy, tell because it has a curly tail, and an ear, I guess, and feet. Only force acting on the pig, assuming it's a slippery enough slide, is gravity. So the only bit of its displacement that we care about is this change in height, h. Reasonable enough. Anyway, so that's a little more complicated. Let us talk about kind of an even more complicated case, where the force is not constant, or the path is strange. You basically have the same problems either way. So we need to kind of rethink what it means to define work in this case. We had said that work was force times displacement. Well, if the force that I'm looking at is taking on this weird curve, then I can't, force times displacement, which force do I take? Well, that kind of invites us to say if we're changing something, we have 2 things times each other like this times force times displacement. It kind of sounds like we're looking at an area. So it kind of makes us want to break it up into Riemann sums, which kind of means what we ultimately want to do is say that work is the integral of force dotted into displacement. But it's going to be the infinitesimal displacement. Infinitesimal displacement. It's the itty bitty teeny tiny super small, doesn't really exist with any kind of finite dimension displacement. So where do we get this? Well, let's take a look at this again. The idea is that for this chunk, if I take this force here times this little delta x, I get an area. if I add up all of these little chunks, I add up all of my little f stars times all of my little delta x's, I would get the work, or something that's approximately the work. I make this smaller, this approximation gets better. So I want to take the limit that delta x goes to 0. And this wonderful thing here is basically the integral. Yay, calculus. Anyway, point is, if we have this wonderful thing going on, we make these rectangles very, very thin, and we do this integral now. So what happens here? Well, now we have to be able to say at every point on the path what the force is and what direction the displacement is. In the most general case, both of these could be weird. This does not happen too often in introductory physics courses. Because if you were to do this such that both were weird, so I have, a path from A to B, which is not this convenient path here, but rather this kind of thing. That path, this screwed up path, basically needs to be parametrized. Also needs a spell check, but you didn't come to this class to learn how to spell words. At least I assume you didn't, because that's a really weird thing to try to take out of AP Physics. Anyway, you need to parameterize this course so that you have a path in terms of one variable, in terms of a whole bunch of variables. And there are ways that may or may not be made easier for you, but again, we'll come to that later. And you also need to know what the force is at all these directions. If the force has some weird, curvy, so if the force is, that's probably the same color that I'm using actually, now that I think about it. Let's say maybe the force is going something like this over here, but then over here it's kind of more like that. And over here it's just totally in this direction, and like that, and like this. And over here, giant arrows, I don't know, and backwards. So if you need to worry at every step along the way what direction you're going in and what the force is, this gets very messy. Usually what will happen, that you'll go from A to B, nice simple path, and maybe the force is changing. Maybe the force is bigger here, smaller here, and kind of goes from big to small, as you go through it. That didn't really work very well because it suddenly was bigger than big and smaller than small. That's one possibility. This is what it's going to look like for a spring. Kind of, although it'll be going that way, but whatever. I'm getting ahead of myself. Alright, point is, this is a takeaway. This is the calculus-based definitions. This is the one that the AP exam wants you to know. So, to recap, work is basically the dot product of force and displacement. For a constant force, for a weird displacement, this works out fine. There's no issues here. It's a little bit of vector stuff, but nothing horrifying. Work, incidentally, is a scalar. Doesn't have a direction. The problem becomes when you have non-constant forces. The key example for us will be a spring. Springs are going to be kind of incredibly important for the AP exam. And we will go into that in more detail later on. But hopefully this gives you some kind of idea of what we're looking at in this chapter. Enjoy.